In this video, we're going to introduce the spanning tree. We're going to talk about the bridging loops and how the bridging loop problem can be solved using the spanning tree. The problem of bridging loops is best shown on an example. Imagine that we had a network like this. Let's say that we had a host A, which is connected to switch 1, host B, which is connected to switch 2, and host C, which is connected to switch 3. Our switches are interconnected in a triangle that looks like this. Now imagine that host A wants to communicate with either host B or C. It knows one of their IP addresses, but it doesn't know the MAC address. So what does the host A do? It sends out a broadcast packet. It sends out the ARP request. This is a broadcast frame which arrives to switch 1. Switch 1 is going to take this frame and replicate it on all of the ports except the port it was received on. Then this frame is going to travel to switch 2 on this link, and switch 2 is going to repeat the exact same process. It's going to replicate the frame to B, and it's going to replicate the frame to switch 3. So this frame goes out this way and goes out this way here as well. Don't forget that we had this frame here as well. So let's take a look at what happens with the frame arriving on this interface. It is going to be sent out to host C, and it's going to be sent out to switch 2. This frame here, on the other hand, is also going to be sent to C, but it's going to be returned to S1 as well. Switch 1 is now going to take a copy of this frame, going to send it to A, and going to send a copy to switch 2. Switch 2 is going to take a copy of this frame, send it to switch 1, and send it to host B. Switch 1 is going to take a copy of this frame, arriving on interface facing switch 2, and send it to, oh, you get the idea by now. What I'm going to end up here with is a terrible loop. Now, this in itself would have not been too much of a problem if we had a concept of, let's say, time to live on layer 2, like a field in our frame that would decrement every time it went through a switch. But remember that switches are transparent devices. They're not going to change the frames in any way when they are traveling through the switches, which means that we don't have such a field. There is no time to live. So this single broadcast packet can actually multiply and multiply and multiply and multiply until our network here completely collapses under the traffic. This is a bridging loop. This is something that we need to try to avoid. Sometimes things are easier said than done. Let's look at our problem here. In our network, we have 3 switches. We have switch 1, switch 2, and switch 3. They're interconnected with these 3 links. A possible reason why they are interconnected with these 3 links is to provide some level of redundancy. Let's say that, for example, this link here between switch 1 and switch 2 fails, so it's gone. Can switches 1 and 2 still communicate? Yes, they can communicate as long as they are able to send the traffic through switch 3. Let's take a look what would happen, for example, if some other link failed. What happens if this link here fails? Can switches 1 and 3 communicate? Similarly to previous example, of course they can through switch 2. And finally, what if this link here between switch 2 and switch 3 failed? Can switches 2 and 3 communicate? And the answer is again, yes, they can, through switch 1. So there was a reason why we configured these switches in a ring like this. This is just one of the examples. So how can we solve the problem of the bridging loop that I described earlier while still maintaining some redundancy in our network? Well, that's one of the things that spanning tree, or STP, is designed to solve. From a very fundamental standpoint, spanning tree allows us to have a redundant physical topology, just like the ring I shown you before, while allowing us to build upon this redundant physical topology a non-redundant tree-like topology, the logical topology that is going to be used by our network, and avoid bridging loops as described. In order to do that, spanning tree needs to elect a root bridge in our network. The root bridge will be the bridge that kind of sits in the center of the network, not unlike the picture that you see behind me, and from this root all other switches can be reachable in a loop-free fashion. So if we take a look at a possible example of that, I'm not going to use this one, I'm going to use a different one. What we are going to end up in a slightly more complex network is the design that may look like this. So we have multiple switches that are somehow spanning through our network, but as you can see, there are no loops in our network. All of these boxes represent different switches, and they are all reachable in a loop-free fashion as long as this switch here is the root. Now, this is the logical topology. Our physical topology can really be anything in this case, but what we are doing here is we are somehow going to make sure that our switches do not forward the traffic on the links that cause the redundancy. So spanning tree is trying to build this logical topology to avoid the loops. Now, how is this going to be done? How is spanning tree going to build this tree? How is the protocol going to operate? Well, we need some sort of signaling, and we need some way to find which are the best paths to reach the root. Spanning tree uses by default the configured bandwidth on the interfaces or the negotiated bandwidth. Like for example, if you had a fast Ethernet that operates at 10 megabits per second, 10 megabits per second will be used to calculate the best path to our spanning tree root. But if we configured on that interface manually the bandwidth using the bandwidth command, this calculated cost of that link would be somewhat different. I'm going to talk about the bandwidth and the costs a little bit later on when we dive deeper into the spanning tree. Also, switches somehow need to communicate who is the root, who wants to be the root, how is this election of the root going to happen, and this is done using special frames called bridge protocol data units, or commonly called BPDUs. Spanning tree, generally speaking, comes in three flavors, and I'm going to talk about all three of them. They are traditional spanning tree, the rapid spanning tree, and the multiple spanning tree. The interesting thing to note here is that even though we speak of traditional spanning tree and the rapid spanning tree as something that is supported by Cisco switches, these two are actually not supported by Cisco switches. Cisco supports their own special flavors of traditional spanning tree and the rapid spanning tree. I'm going to talk about it in a moment. To those of us using Cisco switches, there are actually 5 relevant spanning tree types. These are the common spanning tree, or the one that I call the traditional spanning tree. This is the protocol defined in IEEE 802.1d document, and also sometimes later updated in 802.1q to support multiple VLAN operations. The way this protocol works is we have a single instance for all the VLANs in our network. If we have 256 VLANs, we are going to be using a single spanning tree instance. This is the protocol that Cisco doesn't directly support on their switches because they thought that it was an inefficient way of using the resources in the network. Instead, Cisco came up with their own per VLAN spanning tree plus, called PVST plus, which is a Cisco proprietary approach in which we have a single instance of spanning tree for every single VLAN in the network. That means if we have 5 VLANs, we are going to be running 5 instances of spanning tree. If we have 256 VLANs, we are going to have 256 instances of spanning tree. You may begin to see the problem with this approach from the standpoint of the CPU on the switch. Both of these are relatively slow to converge in a case of a problem in the network, in a case of a failure, link going down or link going up. This has been addressed by the document 802.1w from IEEE and later actually incorporated and replaced the old 802.1d in 2004 version of 802.1d standard. This is called the rapid spanning tree. Rapid spanning tree again runs a single instance of spanning tree for all the VLANs, but the convergence times have been massively improved in a case of a failure in the network. And I'll explain that later on when I actually show you and explain how rapid spanning tree works. Cisco again doesn't support this protocol directly, and instead they have their own rapid per VLAN spanning tree, or rapid PVST+. Again, Cisco proprietary, and we have one instance per VLAN. IEEE very quickly realized that their approach of a single instance of spanning tree for all the VLANs in the network is not very optimum, and they came up with their solution that they called the multiple spanning tree. This was originally defined in 802.1s document and later actually incorporated in 802.1q in 2005. With this approach, different VLANs, multiple VLANs, can be mapped to an instance of spanning tree. So instead of single instance for all the VLANs, we can have, for example, 5 VLANs mapped to instance 1, 10 VLANs mapped to instance 2, and so on. So this is kind of in the middle between Cisco's one instance per VLAN and 802.1d, which says we are going to run a single instance for all the VLANs. So MST is somewhere in between. The important thing about MST to remember is that it requires 802.1w for operation. That means it operates in rapid nature by default. I should also point out that Cisco's PVST and rapid PVST are backwards compatible with their 802.1d counterparts. Also, rapid spanning tree 802.1w is backwards compatible with 802.1d. In other words, these spanning trees can detect if the switch connected to them is running the old protocol, and they can adapt and actually communicate in that network. Multiple spanning tree 802.1s is also backwards compatible with all of the above, at least in Cisco's implementation of this protocol. So how exactly does the spanning tree prevent loops? Let's take a look at the example we had before. We had 3 switches. We had switch 1, switch 2, and switch 3. And they were connected in a triangle like this. Now, when we have a triangle like this, we obviously have a loop, as I described before. So what spanning tree is going to do here, step number 1 will be to elect root. Let's say that for whatever reason, switch number 2 becomes the root. So switch 2 has been elected as root. In step number 2, each of these 2 switches needs to decide which is their best path to reach the root. So let's put this in here, best path to root. And I will explain in a moment how exactly that works. For switch 1, let's say that this interface here is the best path to reach root, and that this interface here is the best path to reach root from switch 3. These ports that are closest to the root are called root ports. On the root switch, these downstream ports here that are facing root ports are something that we call designated ports. and I will again talk about these terms in a little while. These are so-called port roles. There are other port roles, and I will explain them in due course. So now, these interfaces here, the root port and the designated port, they're going to be in a forwarding state. They're going to be able to transmit the traffic. But what about this link here? What should we do about this link here? If this link remains operational on both switch 1 and switch 3, we are going to have the loop as I described before. So we need to find a way for either both or only one of these switches to actually not send the traffic out of this interface. But if we choose to block this port on both sides, on switch 1 and switch 3, what would happen if we had a host here, let's say connected to a hub, that wanted to communicate with the rest of the network? If none of these switches was delivering the traffic to this segment between switch 1 and switch 3, we would not be able to service host A. This is why only one of these switches needs to block the traffic. One of these ports is going to end up being the designated port. Let's choose switch 1 for whatever reason to be designated. But because switch 3 already has a root port and it has a designated port on the segment on switch 1, it will elect to actually block the traffic on this port here. So this is going to end up being a blocking port. So this state here will be forwarding and this state here would be blocking. So what do we have effectively here? What is the logical topology that we end up with? Let's take a look at that. So we had our three switches, switch 1, switch 2, and switch 3. These are the links that are in forwarding state on both sides. And here, what we basically have is this, because switch 3 is not forwarding. If we take a look at this, there is no possibility for a loop forming in this network. The spanning tree did its job. This is all good, but those of you with sharp eyes may have noticed a problem with this approach. Let me show you what I mean. Let's redraw our topology. So this is switch 1, switch 2, and switch 3. Now, let's say that on the link between switch 1 and switch 3, there are no other hosts. It's direct link just connecting switch 1 and switch 3. This is the resulting topology that we are going to have. That means that the link that was sitting here between switch 1 and switch 3 ends up being unused. Now imagine that all of these links here are 10 gig links. That means that we have a 10 gig interface here on switch 1 and a 10 gig interface on switch 3 that are, well, unused, which is a terrible waste. If we were using 802.1d, this would be it. There would be nothing we can do about this. And this is the reason why Cisco came up with per VLAN spanning tree plus. If we used multiple VLANs in our network here, let's say that we had two VLANs, VLAN 10 and VLAN 20. What we could do is, for let's say VLAN 10, we could have switch 2 be the root, and for VLAN 20, we could have switch 1 be the root. In that case, what we are going to be having, let's take a look at that example. So we have switch 1, switch 2, and switch 3. For VLAN 10, this would be a logical topology. For VLAN 20, what we are going to end up having, with switch 1 being the root, this would be a logical topology. So as you can see, we have, this is VLAN 20. So as you can see, for VLAN 10, this is the topology. For VLAN 20, this is the topology. So this link here that was unused for VLAN 10 is now used for VLAN 20. And also, this link here that is unused for VLAN 20 is in use for VLAN 10. In this setup here with 3 switches, with 3 physical links interconnecting them, we have 3 possible topologies. So I already drew 2 possible ones, and this is the 3rd possible topology. So if we had 3 VLANs, let's say that this was the topology for VLAN 30, we would have a very, very optimal use of our resources. But what if we had 50 VLANs in our topology? How many possible logical topologies we have out of this physical topology here? Well, as I said, we have only 3 topologies that make sense. Only 3, not 50. But with Cisco's approach with per VLAN spanning tree, what we are going to end up doing here is we are going to be running 50 different instances of spanning tree to come up with just 3 topologies. And this precisely is the reason why MST was invented. With MST, out of these 50 VLANs, we could map, let's say, 15 to instance 1. We could map 15 to instance 2. And we could map 20 to instance 3. And then we could end up having our 3 link topologies, our 3 logical topologies with our switches, switch 1, switch 2, and switch 3. So this is what multiple spanning tree allows us to do. Now the time has come to actually explore these different flavors of spanning tree in greater detail. So let's do that.